Hey guys, welcome again. Today we're gonna be discussing breakfast search. Just like breakfast search is a graph traversal algorithm as well. Difference is it searches level by level, and it's pretty fast. So with breakfast search, you can find the shortest path really quickly. But it's pretty difficult to implement breakfast search recursively. And the one way, or the conventional way that breakfast search has been done, has been by using a queue. So, as usual, graph traversal is used on graphs, trees, structures, and 2D arrays. So these are the data structures that you might need to apply any of the traversal algorithms on, depending on what you are trying to achieve. So here we got a graph. Graphs and trees are very similar. A tree is just a graph without a cycle. So a cycle occurs when a node can be reached from more than one node. So here we're going to explore what a level means in breadth-first search. Right here, level 1 is going to be the root node. So just like in a graph and tree, node 1 is the level 1 node. Then on the right side in the 2D array, a level 1 could be anywhere on this array, depending on what you're trying to achieve or your starting point. So it could be the number 16 or cell 16, anywhere, depending on where your starting point is. So these are the level 1. Then your level 2 would be any node connected to your level 1 node. So right here, we have the level 2 items. On the graph, it's the node 3, 4, and 2. These are the only nodes that you can reach from node 1. On the tree, 2 and 3, and on the 2D array, all adjacent cells to cell 1. So then your level 3 is going to be everything connected to your level 2. So right here, we have the level 3 items or nodes, which are the ones reachable from your level 2. It continues like this to the entire graph. So one of the ways that neighbors or connected nodes are represented is as an adjacency list. So right here, we've got the nodes and their neighbors. So these neighbors could be usually an array, or usually an array mainly for adjacency lists. For 2D array, sometimes you got to come up with your own algorithm to find neighboring cells. If you guys need a video on that, please let me know, and I will create a video on how to retrieve adjacent cells in a 2D array. So right here we have node 1, 3, 4, 2 as before, node 2, 1, 4, 8, and it continues like that, all down to node 8. So right on the right hand side is the implementation of the breadth-first search algorithm. So the graph here is represented as a dictionary of adjacency lists. So for node 1, as usual, this is just a dictionary representation of what we had in the previous slide. So like I said before, it's the main data structure in breadth-first search algorithm is the queue. So right here we are using the queue class in the Python library. So it's a double-ended queue, which means you can either retrieve from the front or from the back. But in breadth-first search, we're going to be retrieving from the front with the function pop left as seen in the while loop. So I am going to demonstrate the algorithm, and hopefully it's gonna help you understand the algorithm in such a way that you can implement it. It's not really that complex, so it's pretty easy to implement once you get the idea of it. So right here we have the graph. Then we need a queue and a way to mark a node as visited. So right here we're going to use an array for the queue and an array or list as in Python for visited. So what we're going to be doing is we are going to loop until the queue is empty. Right now the queue is empty. So in the code you can see when we execute queue.append root. So root is going to be provided for you somehow or depending on your implementation. So right here, I'm just assuming that the root of this graph has been given as 1. So you could access it by accessing the 1 property of the list, or you can just add a root item and then assign 1 to it. Either of this is going to work, or any other way you can implement it. So root here is just a placeholder. So when we call the algorithm, we actually pass it 1, just like we've done in the middle. So it takes, on the next line, the first line of the function, it takes root, which is 1, and adds it to the queue. Then we execute the while loop. I'm going to skip the loops and the for loops and the while loops because I'm trying to concentrate on the actual algorithm and what's happening inside of it. So right here we pop left, which means we retrieve what's in the queue. So in a variable node, I've just put it there for demonstration. So now the queue is empty. You might be asking, why is the queue empty while? Doesn't that mean the while loop is going to end? No, because right there in the for loop, we're going to add every connected node to node 1 on the queue. So right here, we append the node. So here the action is to print the node. It could be anything. It could be retrieve the node if it's a search. It could be if it's like backtracking algorithm. It could be to maybe mark a place as visited, put something there, or any item. That would be really complex to show a typical example of this. So I've decided not to include that because to shorten the length of the video. So then we go through the for loop. I've marked the 2 lines that are important here. So we add every item or node that is connected to node 1, which is node 342. Now the queue has got an item in it again, and the algorithm returns. The while loop continues. So we pop node 3, as you can see in the queue in the middle. We print or act on it, and then we take all the nodes connected to node 3, which is going to be 5 and 1. But the first line in the for loop checks if that node has been visited. If it has been visited, it doesn't get added. So right here, only node 5 is added to the queue. And we go back again, we pop the next one, which is going to be node 4. Append it to visited after printing it, of course. Back to the for loop. 4 is connected to 6, and the process continues. Now we pop the left, which is node 5, append to visited, pop the next node, which is node 6 now, as shown in the node variable. So this process is going to continue until the queue is empty. Now we pop node 8. As you can see, node 7 came before node 8. This is because either node 4 and 2 were processed first, so it got added to the queue before node 7. So the nodes are going to be added according to their position in the graph or in the tree. We append. Node 8 has been processed. Nothing to add because all the nodes so far have been processed. Now we pop node 7. We append to visited. 7 is gray now because 7 has been processed. Now we check the loop is going to return because there is nothing in the connected nodes which are node 5 or 6 that hasn't been visited. So the while loop checks, queue is empty, and it returns. So I hope I've demonstrated well the algorithm for breadth-first search. Thanks for watching. I hope you subscribe to my channel. I've just decided to do this because I just thought it'd be nice to help someone out there. I know there's a lot of videos on the internet, but maybe that I've got something to offer. So thank you very much. See you next time.